If a hypothesis is untestable, does God exist? That's a matter of faith. And that's a matter purely for religion. Science has nothing to do with it. And so this is how one of the greatest scientists of all time could also be extremely devout. Religion was a matter of faith. Science was a matter of testing. And there's no conflict between the two. Now Maxwell's not the perfect guy. I'll show a little blemish here. He also said later in that letter, "Now I am convinced that no one but a Christian can actually purge his land of these holy spots." I think people of any religion can put science in the testable plot and their faith in the faith spot without any real difficulty. He was very close to his father. In 1856, his father passed away. And he writes here to Miss Jane Kay, his mother's cute little sister. "My father died today at 12 o'clock. He was sleepless and confused at night, but got up to breakfast. He saw Sandy," that's a servant, "a few minutes and spoke rashly, and then came to the drawing room and he sat down for a few minutes to rest and gave a short cry and never spoke again. We gave him ether for a little bit, but he would not swallow it. There was no warning and apparently no pain. He expected it long and described it to himself." His father, he had applied for a position at Aberdeen. He's graduated from Cambridge. He applied for a position at Aberdeen, Marshall College in Aberdeen, which he had not been yet accepted. He was accepted. His father would have been really proud to know his son was a professor at a prestigious Scottish university. This is the final Jemima painting. It is the only painting with Maxwell having a beard. Can you spot him in there? There's Jemima in the center with that pretty blue dress. She loved that color blue, I think. You see Maxwell in there? We'll zoom in. Right in there. He's in there, inside that square. You spot him yet? Right there. He's the only one with a beard. This is the only Jemima painting with Maxwell with a beard. It's a family reunion. Jemima's estate is only reachable by ship. So this is a big event here, everybody getting together. And you can read expressions on every one of these people. They probably, it looks like a jolly little youngster. He looks a little sad. Maxwell, excuse me, look at him. He's a little bit sad here, isn't he? Maybe he's still feeling the effects of his father's death. He was really close. Don't know. At Aberdeen, he gets married to the daughter of the principal of Marshall College. This is a really good political move. The principal of the college is absolute ruler over the entire college, and he's married to the daughter. Yeah, but Maxwell was never one for politics. What do you make of her? Look at the expression there. Ignore the hair, ignore the dress. I don't know what to make of that. Look at it a little closer. I'm uneasy about this one. And there's Maxwell looking down at his wife. Look at the expression on his face. It's an expression of great devotion, I guess. And there's sadness there too. Perhaps this is still sadness from his father's death. Here's a photograph, not a painting, a photograph of Maxwell. This one is frightening. First looking at Maxwell's expression. Fire in the eyes, it's gone. He's still very productive with his research and stuff, but the fire is gone. And look at his wife. Again, ignore the hair, ignore the dress, just look at the face and the eyes in particular. And what I see, and the mouth too here, what I see there is someone who is trying really, really hard to look pleasant but not succeeding. And in fact, while Maxwell, for example, Maxwell had numerous communications, letter communications, with the K side of his family for many years. They all stopped at this point. No further communication by letter with the female side of the K family. She alienated most of his friends. Now, speaking in her defense, too, shortly after, we'll talk about Maxwell getting sacked. Shortly after he's sacked, he comes down with smallpox, often fatal and highly contagious. She knew it. She took care of it. She saw him through that. He's not completed Maxwell's equations yet. He started working on it with Michael Faraday's work, but he stopped that when he's at Aberdeen in Marshall College. And she saw him through another major illness as well while he was at King College. So she took care of her man. And also when running some experiments, thermodynamic experiments, she had to carry great quantities of ice upstairs. She did it for him. So, you know, she took care of her man, but she alienated all his friends as well. And Jemima Memoirs actually have a comment about her. I'll read that. James became a professor at Aberdeen and married a daughter of the principal doer there. This did not give much satisfaction to his friends. The lady was neither pretty, nor healthy, nor agreeable, but much enamored of him. It was said that her sister had brought out the match by telling him, a little complicated here, by telling him how much she was in love with him, and he, being very affectionate and tender disposition, married her out of gratitude. Her mind afterwards became unsettled, but he was always most kind to her and put up with it all. She alienated him from his friends and was of suspicious and jealous nature. I do not think I ever saw him angry or heard him say a word against anyone. While at Aberdeen, Maxwell also starts working on Saturn's rings. Adams had discovered Neptune, or what was the French fellow, Leverrier, or Leverrier. I'm not sure I got the right names. Anybody? 118 times. I should remember this by now. Okay. There'd be a great argument on who discovered Neptune. But the British fellow, Adams, who had discovered not Neptune, Uranus. Okay, Uranus, who had discovered Uranus, set up the Adams Prize for a mathematical problem in astronomy. And the Adams Prize for this year was, what are Saturn's rings? Solid, liquid, or lots of little particles? And Maxwell actually sat down and started working the problem. He figured out that if a solid, to balance tidal differential forces, it'd have to be such a weird mass distribution to be stable. You know, we don't see that, so it can't be solid. If it's liquid, you put a little bit of sideways force on the rings, and the rings will dissipate. It will grow without bounds. It's unstable. Stability theory. Maxwell actually had quite a bit to do with control theory as stability criteria, along with Routh. Routh was a guy who beat him on the tripos, by the way. Routh stability criteria. Okay, so if it's lots of little particles, can you have a stable orbit with lots of little particles? And Maxwell figured out, didn't matter, it's just Fourier series, it really wasn't all that bad. And he came up with this model. He had this model built showing how you could have a ring of moons with an oscillation on them that is entirely stable. Very close to braided rings. Remember braided rings? You put two of these together, you've got braided rings. Pretty cool. And this pays the many-body problem, paves the way for theory of gases. See all kinds of things coming in. Here is a model that still exists today, and they won't let you turn it, but they did turn it and made a movie of it. Notice how the little moons are following a circle as they go around. So there's a braided ring. And Maxwell had it figured out that what the Voyagers and Pioneers would see when they came to Saturn. And that's on display at Cavendish Labs. Bad news. There's two colleges, King's College in Aberdeen and Marshall College, are going to be fused. They are going to eliminate, there's two professors for every position, they're going to eliminate the professor with seniority in order to reduce pension costs. Try doing that today. Maxwell is the junior professor, and he's married to the daughter of the principal of Marshall College. He's got it made in the shade. His competitor, though, Maxwell's nickname was Dafty. His competitor's nickname was Crafty. Crafty gets the position. We don't know why. Nothing to do with Maxwell's very poor lecture ability. And his being married to the daughter apparently didn't help him. So Maxwell's out of a job. And that's something we don't know much about. He tries for a job at University of Edinburgh. Professor Forbes, that family friend, helped him with his first paper. He's retiring. So Professor Forbes, he wants Professor Forbes' position. His friend P.G. Tate here gets the position instead. And they're quite frank. P.G. Tate gets the position because he can lecture. Maxwell really can't. Tries position at King's College. and he's successful. As I mentioned, he had smallpox on the way there. He lived at 16 Palace Gardens. Today is 16 Palace Gardens Terrace, then it was 6 Palace Gardens Terrace. And here's King's College, where he worked on Kensington Park. He often rode horse at Kensington Park. And there's King's College today. And a picture of the inside of King's College as it exists today. While at King's College, he returns to the electromagnetic stuff, but he also starts working with this red, green, and blue. He gets this bright idea. Why don't I take a color picture? I'll take 3 pictures, one in red, one in green, and one in blue, and then project them all together, all at the same time. And I'll have a color picture. This is a wife's hair ribbon. It's a hair ribbon. So I think the knot should be up here, and the things go, and the tails go down. You'll sometimes see it printed the other upside down, which seems a little odd to me, but it's done both ways. These are on display. The original negatives are on display at 14 Indian Street. The filters, they know what the filters were made of, so the filters are recreated. And you combine them together, and there's the world's first color photograph show of the Royal Society by Maxwell. And we're using the same technology, red, green, and blue, to project it today. Maxwell also starts, his electromagnetic theory is starting to develop pretty well, and he's figured out by what we call today epsilon and mu. He had different constants. He figured out by the ratio, what constants he was using, it was the ratio of the electric and the magnetic constants, static constants, gives you the speed of light, square root of that. And he calculated that speed. This speed was measured mechanically, and the modern value is here. This is actually quite common in physics. For example, you can plot the mass of an electron with error bars when J.J. Thomson first measured it. And it'll start up here, and true values down here. Error bars are like this, and over time, you'll see the mass come down to the correct value. And that's because, okay, these famous people measured that, so I better keep doing my calculations until I get something close to that. If I'd gotten that, I would have said I must be wrong. So it's just a human thing. It's what people do. Today, it's a defined constant. No one ever measured it miraculously. Goes to semi-retirement, starts writing his treatise. This is the treatise that we've all known. You can get Dover reprints. It's difficult reading. He's offered a chair at Cambridge. Duke of Devonshire is one of his ancestors was Henry Cavendish. Sponsors Cavendish Laboratory, sets up the Cavendish Laboratory. They asked 2 other people first. They both declined. Maxwell accepted, was the 3rd person asked. He starts writing articles for Encyclopedia Britannica. First one on atom, and then these are the other topics. Here's the article on atom in the encyclopedia. I have the whole set. I'll read the first sentence here. Atom is a body which cannot be cut in 2. The atomic theory is a theory of the constitution of bodies which asserts that they are made up of atoms. The opposite theory is of the homogeneity and continuity of bodies and asserts, at least in the case of bodies having no apparent organization, such as, for instance, water, that we can divide a drop of water into 2 parts, which are each then drops of water. And so we have reason to believe these smaller drops can be divided again, and so on and so on. He has to give lip service to the idea that atoms don't exist. The existence of atoms have been suspected since I think it was 600 BC, but not proven. When was it proven? Anybody know when it was proven? Einstein's work with Brownian motion. That was the proof atoms existed, 1905. So, and it does a theory of rarefied gases too. By this time they figured out that light must have pressure, must put pressure. So, okay, we'll test the theory. This is science. It's not faith. That's religion. This is science. We test the hypothesis. If it fails, we throw out the hypothesis. If it succeeds, then we go on and try to break it again. Okay, we built a little bottle with no air in it, put a little windmill in with flags on it, white on one side, black on the other. Light will hit the white side and bounce off, and it'll be absorbed by the black side. So it'll go white pushing, black leading, going around and around. Great, we'll build it. We'll put it out in the sunshine. Whoa, excellent, Maxwell's right. It's going around, oh, wait a minute. It's going much too fast. We didn't predict it was going that fast. Hold on here. It's going in the opposite direction. It's not, it's black pushing, white leading. Why is this? it's going the wrong way. And a fellow by the name of, okay, this was Reynolds. Okay, I got it mixed up from earlier. Reynolds, this is Reynolds with the Reynolds number, came up with the idea of rarefied gases that it's just rarefied gases in there. This is oversimplified, but good enough for now. Black is hotter, and the rarefied gases are bouncing off faster than the white side, which is cooler. So black will push, white leaves go round and round. And he writes up a paper on it. Maxwell's a reviewer. Maxwell writes a scathing review, sends it back to him. Then Maxwell takes Reynolds' ideas with attribution and publishes it. Reynolds is livid, and Stokes tries to settle the argument between them. He tells Reynolds, "Hey, Reynolds, back off, okay, will you? Maxwell's terminally ill. Give him a break." There's Cavendish Laboratory today, the old Cavendish Labs, which is no longer occupied by Cavendish Labs. Maxwell faded for several years. At his deathbed was longtime friend Colin McKenzie. He reports, "A few minutes before his death, Professor Clark Maxwell was being held up in bed, struggling for breath when he said slowly and distinctly, 'God help me, God help my wife.' And then he turned to me and said, 'Colin, you are strong, lift me up.' He next said, 'Lay me down lower, for I'm very low myself, and it suits me to lie low.' After this, he breathed deeply and slowly, and with a long look at his wife, passed away." James Clark Maxwell died at the age of 48 of stomach cancer, the same disease that took his mother, at the same age, precisely 40 years earlier. This is his tombstone, put in place by lawyers. There's no loving memory of or anything. It is in the ruins of a 1500s era kirk or church. Maxwell added displacement current. He put Faraday's work in mathematical form. No vector operators used. He had 21 equations and 21 variables. No divs or curls. Introduced the field concept mathematically. Faraday introduced it qualitatively. He said vector potentials are primary. The form we see today was developed by Heaviside and Hertz. Heaviside has priority. Heaviside on top. Read those odds. What kind of person was he? He was really cranky. Absolute self-taught mathematical genius. Never went to university. We're very fortunate to have him, but a lot of his work was suppressed because he did not do the politics at all. And Heinrich Hertz died at the age of 36. Horrible genetic disease. His face was kind of melting away. Very painful. He did not deserve that. Imagine what Maxwell Hertz had lived to a normal age. Heaviside died at 70-something, was pretty senile at that time. Why do we have magnetic vector potential, which is what Maxwell put primary as symbol A? Well, this is out of the treatise. Maxwell viewed it as primary as A. A is primary. The magnetic field, B, is derived from A, so B is secondary. That's my personal interpretation. I've seen some other creative interpretations as well. And remember the circles on that floor? There they are. This was Maxwell's model of the luminiferous ether. He did this in 1855. He later completely threw it out, did not do anything with a mechanical explanation either, because you just can't extend this to 3 dimensions. There's cases where what do you do in a vacuum? And this is like atoms. These are like electrons. You can pull them out in a dielectric, and then they have like a spring. We'll pull them back in. There's the displacement current. So it works really well. So that floor, it's his model of the luminiferous ether. Statue was unveiled in November of 2008 on the end of George Street. Off to the right and back is on the big pillar is a statue of the guy who invented income tax. So if you've got a strong arm, you can throw some rotten eggs up. Go right ahead. Very near the Royal Society. By all means, visit. I got a nice article in IEEE Microwave Magazine. I can send you a copy if you want. About the plinth here and the detail. There's his dog, Toby. There's his whirling disc for color. In conclusion, Maxwell freed us from the womb of Newtonian mechanics. He presented these equations, threw away the mechanical model. We don't need an F equals ma. We just got these equations. They work really well. Take the equations or leave them. It took 23 years before people would believe them. And that's a whole other presentation I can make. But he completely removed us from that womb of Newtonian mechanics, which was really constraining things. Set the stage for all the amazing triumphs of 20th century physics. I'll read from Freeman Dyson. Freeman Dyson is one of the other architects of, he's still living, of quantum electrodynamics, along with Richard Feynman. The ultimate importance, according to Freeman Dyson, of the Maxwell theory is far greater than its immediate achievement in explaining and unifying the phenomena of electricity and magnetism. Its ultimate importance is to be the prototype for all the great triumphs of 20th century physics. It is the prototype for Einstein's theories of relativity, for quantum mechanics and quantum electrodynamics, and for the unified theory of fields and particles known as the Standard Model of Physics, of particle physics. All these theories are based on the concept of dynamical fields, introduced by Maxwell in 1865. Yes, we do indeed stand on the shoulders of giants. Thank you.
Thank you very much. I have one question. I believe that a lot of his work was one of the motivations for Einstein, especially on the special theory of relativity. And I know that, I wanted to ask you your opinion. I know that it's often attributed that Einstein said, is it God who wrote these lines? Although it wasn't in the vector form, but I was wondering about, is that correct or not?
I don't know about that particular quote, but I do know there's a very easily, you can go on the internet and get this picture of Einstein sitting at his desk in Princeton with a picture of Maxwell up in the right-hand corner. Another story I've heard is that Einstein, who didn't like to give presentations, at one point was asked to come and give a lecture at the Royal Society, and he said he would accept on one condition, that he could walk in the same floorboards that Maxwell had walked on. If you read a biography of Einstein, Maxwell's equations, Maxwell's electromagnetic theory was the prime source of thought experiments that he ran as he was starting to explore the theory of relativity. Imagine riding a bus in Zurich and the clock, and a beam of light comes from the clock, and imagine the bus is going the same speed as that beam of light. So these are the kind of thought experiments that propped up. And one thing that's absolutely amazing is Maxwell's equations were, as Maxwell wrote them, were all ready for relativity. There's no changes there's no relativistic form of Maxwell's equations. It's already there. Is that awesome?
Thank you so much. Thank you for that very personal perspective. I think all of us, when we run these calculations again, will have a little bit of a different perspective. On behalf of the AMTA organization, we'd like to present you with this certificate of appreciation. And we've also got a small gift for you.
Oh my goodness.
So again, do we have any additional questions from the audience? I think we have a few moments. Anyone have anything that they'd like to add or any questions of Jim?
There is a second equation there.
Oh, you're tough. Sorry. Okay, second stamp?
No, the fourth one.
Fourth one, okay. Oh, yeah. That's the Heisenberg uncertainty principle.
Yeah, so there's not just
Yep.
zero equation, but two actually.
Oh, good point. Very good, very good. Excellent. You're the first person, 118th time I've given this, you're the first person that pointed that out. Thank you. Oh yeah, I said there was one equation at the beginning. There was one equation in my entire presentation. It's just pointing out there's a second equation.